much, and I'd like to thank everyone for the opportunity to come speak with you this morning. I'd also like to thank Dr. Martin for the very insightful presentation earlier. We'll actually see some of the potential applications of those concepts in terms of what we do at the IV&V program in Fairmont. And please excuse me, I'm somewhat tethered to the computer here. I don't have a clicker, so I'll just advance the charts from here. So I'd like to start the presentation with a little bit of background about IV&V in general, as well as the origins of IV within NASA. And the reason for this is there are different types of IV&V. You have hardware IV&V, you have software IV&V, you have IV&V from an integration standpoint. But in addition to that, you have different flavors within various domains in terms of application. Refer to some as a heavy application of IV&V, a standards-based, very rigorous application, to a lighter application which is focused more on oversight of the developers' activities and processes. So we will share some insights on both of those approaches. So the NASA IV&V program is a branch of the Goddard Space Flight Center, as well as the NASA Office of Safety and Mission Assurance. We're located in Fairmont, West Virginia, as you saw on the first chart, and we were established in 1993. The genesis of our program actually came out of a very unfortunate event, which was the Challenger disaster in the mid-'80s, which many are probably aware of. Now, the Challenger disaster obviously wasn't attributed to software. However, as a result of that, and the report that came out of that was the Aldrich Commission report, actually called for various forms of oversight from an independent perspective. And one of those was software IV&V. And over time, this has been reinforced by a number of different factors. And in many cases, some very unfortunate failures that have resulted in both the loss of property and mission, as well as the loss of life in a non-NASA domain. Individuals may be familiar with the Deadrick failures that resulted in a number of people being radiated inadvertently during radiation treatment. We have a number of instances where we've had glitches or failures that have resulted in loss of data, in some cases loss of actual missions. We had the Ariane 5 failure due to an overflow error in the software, and we continue to see these. So, and as systems become more complex, as software becomes more pervasive, we just heard Dr. Stephen Hawking talk about one of the greatest threats to mankind may actually be artificial intelligence from a software perspective. So as we see the more pervasive use of software in our systems, the need for additional oversight and insight into the software development becomes more and more critical. So for the purpose of framing this discussion and ensuring that we're on the same page in terms of what is IV&V, I thought I would give our viewpoint on IV&V from a NASA standpoint. So IV&V focuses obviously on three independent perspectives. Independence from a technical standpoint, from a managerial standpoint, as well as from a financial standpoint. As we have seen over the years, IV&V has been applied in both what I'll call the big perspective, which is true independence from a technical, managerial, and financial standpoint. Oh, actually, could you go back just one shot here? As well as from what I call a little I standpoint, which is in cases where maybe one of these perspectives is jeopardized. And that tends to happen primarily from a financial perspective, where the organization funding the IV&V is the same organization that is receiving the IV&V services. NASA has sought to avoid that by funding the IV&V facility independent from any of the missions or the mission directorates. So we attempt, even though we are funded by the same umbrella organization, to remove the funding entities from a stakeholder perspective from the action. Now, whenever we're applying IB&B, we tend to focus on 3 perspectives. And we focus on these from a systems standpoint, which is looking at the system from the perspective of, does it do what it's supposed to do? Does it not do what it's not supposed to do? And does it respond appropriately in the presence of adverse conditions? Now, you could ask yourself, how do you do this? Certainly the goal is to not do this exhaustively, especially from the second and third perspectives, because as you saw, as the number of entities in the system increase, as you focus on additional perspectives like interactions, the operational environment in which it actually has to function, that state space can explode very quickly. So the idea is to focus these perspectives in the context of the actual system that you're looking at and understanding what are the most critical aspects and most critical perspectives that you're trying to assure. We like to look at it from a risk reduction standpoint, meaning that whenever we're performing IB&B, we try to ascertain what are the key risks to the system and to the software, and how do we go about actually mitigating those risks through the performance of our IB&B activities. Any activity that we do should be contributing to the mission in a risk reduction standpoint. So every dollar that we spend should buy down some degree of risk to some degree, or every hour that we spend doing analysis, doing additional testing, applying formal methods, whatever it may be, is designed to actually drive down risk. So over the years, we have established a number of best practices. We have what we call our IB&B technical framework, which actually has its origins in IEEE 1012. In addition to that, over the years, we have built what we call a catalog of methods, which you can think of as low-level work instructions that actually talk about how we implement the higher level principles within our technical framework. And the idea is to apply these across the full course of the software development lifecycle. Now, with that said, one of the principles that we try to adhere to is being tailorable, in that we tend to, we try to focus our efforts in a way that's going to be most advantageous to the actual project. So by learning what the areas of risk are, we may actually decide that for a given entity that it's appropriate to only focus on requirements and tests, or it may be appropriate to only focus on model checking of the software, or run a prover against a subset of the code. It depends on what it is we're trying to assure. And that's what we're going to talk about here in a few minutes with our IB&B assurance strategy. This assurance strategy is our approach for providing assurance to the mission, to the Office of Safety and Mission Assurance, as well as to the agency as a whole. So to do this, we have an assurance strategy that is established specific to an individual mission. It's implemented via an assurance design, and it's communicated via assurance statement. So we intentionally overload and overuse the term assurance because we're trying to drive home the concept that we're trying to achieve here. So what is IB&B? So, specifically, what is an assurance strategy? So our assurance strategy is the selection and implementation of the IB&B verification and validation processes. So over the course of a life cycle, we may implement any number of processes or methods from our catalog of methods, and we may and do tailor those to the needs of the individual project. The idea with an assurance strategy is understanding what each project needs and what risk needs to be locked down on an individual project, and how do we go about doing that. And one of the things that we struggle with frequently is a lot of our practitioners are looking for more of a checklist-driven approach to performing IB&B. And there are certainly in some environments appropriateness of using checklists. So, for example, for those that have ever flown a plane or sat in a pilot seat, you know that you have a very specific and rigorous checklist that you go through whenever you're preparing for flight, as well as preparing for landing. And that is appropriate. complex software system, a checklist approach is not always appropriate for determining what assurances we need to provide. It is a list of options, but not necessarily a list of options that are going to be applied on every single project. So we'll talk about how we go about assessing the risk and looking at it from a systems perspective and how we use that to focus our analysis. In addition, one of the underlying tenets of how we approach I&D is the collection of empirical evidence. So, and we'll go into this more detail, but the general concept here is that whenever we make assurance claims or assurance statements, we want to have evidence to back that up. We want to actually ensure that the analysis that we're performing provides adequate data that we can share with our stakeholders to give them the confidence that we have brought down the risk in the right areas. So, how do we go about actually doing I&D? So, as I mentioned earlier, there are many different forms of I&D, and really, it's going to vary from organization to organization, but the I&D and application of it should be tailored to what it is that you're trying to assure for that project. So our process includes assessments, analyses, evaluations, reviews that are ranging from full lifecycle reviews to module level reviews, inspections, and testing of the software artifacts that are created throughout the course of the lifecycle. During the performance of these various techniques, we utilize the collection of evidence to formulate recommendations that improve the quality or reliability of the software systems. We utilize evidence to make conclusions about the quality or reliability of the system software. We also use evidence to gain insight into the technical progress throughout the performance of the development activity. And we use evidence to judge how thorough we critique the actual system. So the evidence actually enables us to look at all the work from multiple different perspectives. So the one looking at from the perspective of how well the developer has done in implementing the system, as well as how thorough and rigorous that we've been in the application of our techniques. Now, a key point that we struggle with, and I do not have an answer for, is how much evidence is the right amount of evidence to collect. And it's the same thing from a rigor perspective. And you can think of rigor and evidence almost going hand in hand. And really it's driven by the criticality of the system and the degree of risk reduction that we want to actually perform. So, for example, you have systems that are much more critical in nature and have, for example, human-rated missions have much more critical subsystem components that are going to warrant an increased level of rigor or more formal approaches than maybe a less critical component of a science mission where human life isn't at stake. Certainly, you can still have safety mission critical software, but nevertheless, you have a different degree of criticality for those systems. So the understanding of those systems and what it is we're trying to achieve allows us to determine how much rigor we need to apply and how much evidence that we need to collect. So to do this, we actually perform a risk-based assessment of the system. So we refer to this as our PBRA, but what we're trying to assess is the inherent risk associated with the system capability. So whenever we're performing I&D, as you heard in Dr. Martin's presentation earlier, it's critical to look at the system from a true systems perspective and not look at it from it's this thing, it's this entity in front of us. So we need to understand the environment in which it needs to operate. We need to understand the objectives in which the mission actually has to fulfill to be successful. We need to understand the various stakeholders that are involved and what areas are of concern to them. So whenever we're performing this assessment, what we're actually looking at is, from a whole system perspective, what capabilities must interact together to fulfill the mission criteria to achieve success. What entities are responsible for working together to interact and to providing data and information. information to successfully execute those capabilities, what low-level behaviors are necessary, what emergent behaviors exist within the system that the system operators need to be aware of, and so on and so forth. So through the application of this process, so I'll walk away here for a minute with the microphone. So whenever we're performing the PDRA process, what we'll actually do is we will utilize information that's made available to us by the system developer. For example, high-level mission specifications, documents like CONOPS, early trade studies that were performed, so on and so forth, to actually formulate our own understanding of what comprises the system, what the system has to actually do to be successful, and what we develop. And there are times where this may be synonymous with how the system has the system developer has defined their capabilities. Sometimes it may be a different viewpoint. And it all determines on what it is that we're trying to assure. In some cases, you'll see, like you see here, a definition of capabilities that are more driven by the mission phases. That's not always the case, but for this example, it's a little easier to explain. But what you see here is we have some high-level capabilities for this, and this is, as you'll probably deduce, is for a Mars mission. It's a Mars mission that actually launched. It would have been in 2012. And so we have a set of high-level capabilities that are focused on launch, cruise, approach Mars, maintaining the flight system throughout the cruise phase, as well as through all operations, EDL, as well as surface ops. And we have EDL, which is our entry, descent, landing, and then the performance of surface ops. Now, within each one of those, you have a set of lower-level capabilities. And your decomposition is certainly going to be iterative in nature, and it may go multiple levels deep. For ease of communication here, we just have 3 levels deep, and we only went 3 levels deep on one of the actual sub-capabilities. But there may be a need, depending on what it is you're trying to assure, to drive down multiple levels to ascertain what are the necessary capabilities of the system. And we start looking at this from a system perspective, but then we certainly need to roll in software as the software IPV entity. So that's where we start looking at the responsible subsystems to perform these higher level capabilities. So as a part of our process, and actually I'm going to make this available to now, we actually have a published process for performing our PDRA. What we do is after we've identified and defined the capabilities, we'll perform an association between the capabilities and the entities within the system that are actually responsible for fulfilling those. Now, this is just a very crude mapping that shows the higher level capabilities, but this is certainly decomposed much farther. And from a software perspective, many times we'll actually get down into the module level. We're associating individual modules or software domains to the higher level capabilities. And why that is so critical is it gives our engineers insight into what those lower level entities must do to support the overall mission. What interactions are necessary? What data needs to be provided to other components or other entities, thinking of it from a services provided, services expected standpoint. And as a part of fleshing this out, as I said there, this is a very high level. We'll use numerous tools that we have at our disposal, whether it be SysML, UML. We'll talk a little bit about insurance cases here momentarily, but we'll utilize those tools to help us better understand the system, what the system must achieve, and what is required from a functionality standpoint to support that. So after we do this definition, we actually apply a set of standardized criteria that allow us to what we call rack and stack them. So what we use here is just a very simplistic 5x5, and it's simplistic intentionally to help aid in the ease of communication and show from a risk perspective, because one of our goals as an assurance organization is to buy down risk, to show from a risk perspective what we feel are the primary challenges or risks to mission success. And so these are the areas that we're going to focus on. Now, we show a little bit of a distribution here. We didn't map everything, but typically something that falls into the green, we will not apply any degree of IB to it. At that point, it's thought to be low risk. There may be cases where we want to look at maybe just a very small component of it, maybe something, if it was up in the higher likelihood that can help drive it down a little bit, but that's very rare. Typically, we're only focusing on items that fall in the yellow and red. Now, what that does is that is just an indicator or a starting point for helping us determine how much rigor and evidence is needed. So, and this is where I caution people when they ask for trying to use a checklist. I've had people come to me and say, why don't we just develop, or why don't we as an organization develop a standard set of processes or activities to perform if something falls in this block or in the yellow or dimmer? Well, the reason that I caution against doing that is there's no one right answer for the mission. You have to understand what actually drove that risk. What were the things that, when we look at our criteria and develop the rationale against that, what did the rationale say put this here? Those are the risks that we're trying to mitigate. And the same for something that's going to be in the red. Now, as a general guideline, something that falls a little bit lower from a criticality standpoint is going to get a little less rigor. But again, that is very subjective and depends on the nature of the system. And we encourage people, we're engineers for a reason. We think about things very logically and critically. So we encourage people to utilize those tools and those skills that they developed through the course of the career as well as in school, and apply that to understand what is needed to buy down this risk. So, for example, if we have something that maybe falls down in the lower part of the 5x5 there, we might determine that some manual analysis or static analysis of the code is adequate to buy down the risk far enough to get it to an acceptable level from a residual risk standpoint. If something falls up here, we might determine that we need to do more dynamic analysis or independent testing or more formal analysis, maybe even to the degree of model checking or using one of our analysis tools that is more of a prover-based tool to actually mathematically prove the absence of issues to give us increased confidence in the system. So actually, I talked about several of these points here, but our assurance strategy is implemented through the assurance design. So when I talked about the PDRA process and how we go about understanding what are the inherent risks to the mission, the next step is determining how do we go about actually putting a plan in place to mitigate that. And so that's where some of the discussion on determining the amount of rigor and the degree of evidence that needs to be collected comes into play. So the assurance design is actually the steps that we go through to determine what are the specific methods that we need to apply. I talked about our catalog of methods. So for a given system, we may go down through and say that methods X, Y, and Z are necessary to support this assurance strategy to make up this assurance design. We also have a component of our assurance design that's referred to as our technical reference. So why this is important is the technical reference captures our expectations of the system and our expectations of the software. So think of it from the perspective of if someone asked you to proofread your paper on a concept and to share your thoughts before you had an opportunity to formulate your own thoughts or write your own papers. After reading that, you're going to tend to fall into a groupthink perspective and are going to be more likely to follow suit with the concept that they lay out. However, if before you do that, you formulate your own thoughts and your own perspectives and document those, now you have a point to compare against and provide more valuable, more meaningful feedback. And that's what we try to do. Now, we don't try to replicate the entire set of specifications for the system. And in some cases, the actual specifications and high-level concept documentation will be rolled into our technical records. But at the end of the day, we supplement that with our mission understanding. We roll in heuristics from other projects as well as previous experience that we gathered, and that formulates our technical reference, which is a very critical component of our assurance design. So now, over the course of the IB&V effort and the performance of the analysis, the application of the methods, we generate large amounts of data. Now that data is critical in that it flows into our actual assurance statements that we provide at various points throughout the life cycle. Assurance statement is just a very simplistic concept. What it is a summary statement that communicates what it is we have assured about the project, or what risk that we have reduced throughout the performance of our IV&V services. And we try to keep it simplistic because we wanted to just focus on the actual concept, which is we need to very succinctly communicate to our stakeholders what it is we have assured and why they should have confidence that the mission should not, or if it's earlier in the life cycle, why it should move from phase B to phase C or phase C to phase D, and so forth. So now we back that up with a tremendous amount of data, but we don't want to throw that data on all the stakeholders and allow them to draw their own conclusions. We want to conclude for them and summarize for them what it is that we have seen through the performance of our analyses. So we have numerous tools for implementing our assurance strategy, and I actually, for the sake of time, want to skip ahead a little bit here and talk about some of our more recent advances and tools and more recent focus areas. I've already touched on the catalog of methods, but one of the areas that has become of increasing interest to us as an organization as well as an agency, especially recently, is cybersecurity and information assurance. Seems like every time you turn on the news, you're hearing about some type of hacking event that has taken place, some type of system that has been jeopardized, whether it be an information system, whether it be someone's Twitter account, whatever it may be. Some have more impact than others, but nevertheless, something has taken place in that system that has allowed someone to gain access to it. So one of the things that we have rolled into our portfolio is the capability to aid our customers in cybersecurity and information assurance. So I've broken this out into 4 quadrants here. Actually, I borrowed this from one of my colleagues who broke it out into 4 quadrants. But we focus on it from the perspective of threat and risk assessment, vulnerability assessment and penetration testing. IV&V in-phase I stands for information assurance support, and we have a cyber lab that helps us perform each one of these. So from a threat and risk assessment process, think of this as more maybe like a consulting perspective. We help people with physical compliance. We aid them in full life cycle compliance evaluation, and we've aided people in getting what we call in the federal government in the states an authority to operate. So in addition to that, we will do in-phase support, which think of this as more like traditional IV&V, where throughout the performance of the software and system development activities, we're looking at ways to help them build security in from the ground up. We're looking at providing ways to help them verify that the architecture that they have in place is not one that is prone to security attacks and invasion. And we're doing that through the application of various IV&V methods that we have in place. We also have ways to help people perform, or we can perform for them, vulnerability assessment and penetration testing. So in those instances, we're looking at the implementation of security controls, monitoring of security controls, and one of the ways that we can do this in a non-operational system is actually through static code analysis. There are many commercial tools out there, albeit some of them quite expensive, that have the ability to check for things referred to as common weakness enumeration, other laws in the code like buffer overflows that hackers can exploit to make the system more vulnerable, as well as custom checks that we have wrote based on things that we have observed through those many years of work that can potentially leave a system vulnerable. And we've also established a cyber lab. So this is a component of a lab that we've had in-house. We'll actually talk about on the next chart for a number of years that we refer to as our JSTAR lab. It's our independent test capability. And we've extended that to allow us to play more effectively in this cybersecurity and information assurance domain. We have made great strides in the ability to virtualize servers and systems to allow us to perform testing off-site. People tend to be a little bit nervous about this because basically what we're doing is you're going out imaging their whole system, bringing it in-house, and we're testing the daylights out of it from a vulnerability perspective. The nice thing about this, we're not going to break an operational system, especially systems where they can't afford downtime. They might not have redundant systems that they can switch over to allow testing and so forth. We have a number of penetration test tools, tool sets. We have a very extensive cybersecurity knowledge base. We've actually developed a cybersecurity training that we've allowed a number of people to participate in. Most recently, some of the National Guard members that have increased their, or trying to increase their capabilities from a cybersecurity perspective, and then also increasing capabilities from a mission system virtualization and testing standpoint. So another area that we have invested in significantly over the years is our ability to do independent testing. One of the things that we found is that we can only do so much manually, we can only do so much through static code analysis, and we can only do so much through the application of formal methods. At some point, you have to actually look at how the system's going to operate, how it's going to operate in an environment in which it's actually going to fly, and what can we do to increase the confidence that it's actually going to perform as expected, not perform as not expected, and respond appropriately in the presence of adverse conditions, those three tenets that I referred to earlier on. So we've established a test capability that allows us to perform simulation, automation, independent testing, and virtualization. And for the sake of time, without walking through each and every one of these, what we have tried to do is provide and develop for ourselves a capability that allows us to essentially test a software system as early in the life cycle as possible. Now, for many, many years, software developers have had desktop test rigs or test capabilities from a software perspective to where they can evaluate small components of the software. But to evaluate and test the entire system, frequently you're going to need a full test rig or a SIM that is composed of some components of hardware, the actual board that you're running on, maybe various other components, boxes that simulate the actual instrument, so on and so forth, but there's some combination of hardware and software. What we have tried to do is get to the point where we can emulate or simulate nearly every part of the mission to allow for testing much earlier. And we're able to do this at various levels of fidelity, depending on the amount of architectural information, how much specification is actually available to us. So, for example, many NASA projects fly a RAD 750 board. So it was a safe bet for us to go off and procure components of and develop components of ourselves, an actual RAD 750 emulator that allows us to basically observe the execution of the software down to the instruction level and run that in our lab. We've developed a number of components that people can utilize to perform testing at various levels throughout the development lifecycle. But the whole idea here is to have a capability that we can provide to our analysts as well as to our customers on the mission side that they can use earlier in the life cycle to gain increased confidence in the software that it will perform as required. Now, actually, I don't know if I'm going to be able to get to some of the insurance case data that I'd like, but I can certainly talk to anyone more so afterwards about our use of assurance cases if desired. But I'll summarize from the perspective of the benefits of IBM. As I'm well aware, folks are very familiar with IBM, but I always like to reiterate there are skeptics out there in terms of the benefits that we can provide for a mission. So, a successful application of IBM and a successful definition of an assurance strategy, a successful definition of assurance design, and successful communication and development of assurance statements allows us to provide the confidence that the software products are error-free and meet the needs of the user. It increases the likelihood of uncovering high-risk errors earlier in the development lifecycle. As everyone's well aware, there's n number extensive. But the general premise there is the earlier you identify and communicate a issue, the earlier it can be fixed at a lower cost. In addition, we provide some intangible benefits, which is very valuable to our stakeholders to be able to communicate at various points throughout the life cycle, ongoing indicators regarding the performance of the development efforts, both from a system and software perspective. And these are merely inputs into a large set of data that's used, for example, at milestone reviews, like a PDR, a CDR from a NASA perspective, or maybe even a decision to delay development, delay the launch, or to actually launch. So we participate in their flight readiness reviews, mission readiness reviews, SMISRs, and so on and so forth. So we provide these data points to the stakeholders so they can make a more informed decision with regards to how the development effort has proceeded. In addition, by doing this earlier in the life cycle and providing these ongoing indicators, we give people an opportunity to make adjustments early when it is cheaper instead of doing it later on. Also, one of the things that we try to do is facilitate the transfer of system and software engineering best practices. We've been in a very lucky position in that we observe the software development and system development practices across many different developers, across many different systems, actually across, in some cases, various international partners. So what that allows us to do is, without compromising the proprietary nature of any data or individual developers' approaches, we're in a position where we can communicate industry best practices to developing software, to developing systems, to detecting faults, to collecting evidence, to ultimately provide confidence that the mission will perform as expected. And at the end of the day, we firmly believe that if you have an effective assurance strategy, assurance design, and carefully and correctly constructed assurance statements, we can provide an IBOV service, or anyone can provide an IBOV service that leads to higher quality products, reduced risk, greater insight, reduced costs, and increased knowledge transfer. So being mindful and respectful of everyone's time, just